In this video, we're going to be looking at the two special right triangles. Okay, and one of the reasons that we're going to be looking at this is because Pythagorean theorem has some limitations to it. The limitation to the Pythagorean theorem would be that you would have to know two of the side lengths so that you can figure out the third one. That's literally the only way that you can approach it. However, we've got these two special cases where if you know one value, you can actually figure out the two other ones. All right, so the first case is what we call the 45-45-90, or the isosceles right triangle. Okay, the 45-45-90 refers to the angle measurements that we have. So this would be a picture of it here. The 45 degrees would be located here and here. They'd be located in those two spots. Now, this would also be an isosceles right triangle because if these two angles are congruent to each other, that would mean that the side lengths across from them would be congruent as well. Hence, we have an isosceles triangle. All right, so where you really want to see this come from is a square. Okay, now what I had mentioned is that it does have 45-degree angles on there, but this shape itself is also just half of a square. That's what it is, it's half of a square. If you took a square and then divided it using the diagonal, you would get that, and then you'll probably see here that it makes sense that you get 45 degrees here, because if we split that evenly, you get 45 and 45. All right, so consider it as a square to begin with, and that would mean that all the sides are congruent. You'd have x, 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 and x. By the way, I'm using x just as a representative number. Okay, it doesn't actually have to be a value here for what we're going to eventually figure out, which is this. If you have a leg length of x, like these here, if you have those, the hypotenuse is going to be x times the square root of 2. However, we are going to prefer using the square root of 2 for this. All right, now why is that true? Why does this actually turn out to be x times the square root of 2? We can figure it out using Pythagorean theorem. Okay, Pythagorean theorem says, well, we write it as a squared plus b squared equals c squared. But what that means is that if you took the leg lengths and you squared them, you then added them together, you would get the hypotenuse squared. Okay, in this particular case, the leg lengths a and b are actually both x. So we would have x squared plus x squared. Okay, and those turn out to be like terms. These are like terms here. So we can write this as 2x squared is equal to c squared. And now what we would normally do at the end of a problem is take a square root to get the hypotenuse. So I'm going to go ahead and square root both sides, which would look like this. And that would give me the hypotenuse. Now, rules to radicals and how you square root things. If you have any factors that are inside that are perfect squares, you can actually square root those, such as the x. I can square root that and move it on the outside of the radical. But because the 2 is not a perfect square, that would actually just stay inside. And that is the length of your hypotenuse. So given any length here, you can actually multiply by the square root of 2 to get the hypotenuse. Or if you have the hypotenuse and you're aware that this is the type of triangle you've got, you can actually divide the hypotenuse by the square root of 2 to get the leg lengths. All right, for example 1, what we have is an isosceles right triangle, or what would be called the 45-45-90. We know that because you've got a right angle here, this would be 45 degrees, so the rest of our 180 would have to be 45. All right, so we have an isosceles right triangle, which means that we can apply the rule that we just looked at. We could take a leg length and multiply it by the square root of 2 to get the hypotenuse. In this case, that's not what we want to do because we actually have the hypotenuse. So instead, let's go backwards. Let's go backwards with this. Let's take the 8 and divide it. Let's divide it by the square root of 2 to get the length of x. All right, so 8 divided by the square root of 2 is going to give us 5 points, let's do 2 decimals, 5.66. All right, so that's the whole problem. That's it. That's all you got to do. That might actually explain why we call this special right triangles, because all you really have to do here is either multiply or divide by the square root of 2. It's a shortcut. Think of it that way. You have a shortcut that you can apply for this particular type of a triangle. As the title would suggest, we have two special right triangles. So this is going to be our second one, which we just called the 30, 60, 90. We don't have another name for that one. Okay, this is the 30, 60, 90 right triangle, which would mean that the angle measurements are 30, 60, and 90. All right, now where does this come from? The last picture that we looked at, the isosceles right, was actually half of a square. It was half of a perfect quadrilateral. What we're going to look at is the perfect triangle, the equilateral triangle. And if we split that in half, we're going to end up with some shortcuts as well. Okay, so let's think about what happens when we actually do split this in half. Okay, so if it was an equilateral triangle to start with, that would mean that all the sides are congruent and that you've got 60-degree angles in each of these corners. That one I'm not going to write yet. Okay, you'd have 60-degree angles in all the corners. But if we truly split it in half, that top 60 degrees is going to break into 30 and 30. Okay, and then don't pay attention to that side. That doesn't matter, because really what we want is to talk about the 30, 60, 90, except that it is important that it does come from the equilateral triangle. For instance, the length of this segment right here in the 30, 60, 90, I'm gonna add that in there too. All right, the length of that part, what we might call the shorter leg, that right there compares nicely to the hypotenuse, because the hypotenuse is this total base length here, okay? So that short leg is actually half the length of the hypotenuse. So we've already got a connection there. We have that part. Now, if I look at the prompt that I have up here, it says that what we need to do is show that if the shorter leg has a length of A, so let me add that in. If it has a length of A, then the hypotenuse is 2A. That part we've actually already figured out, right? Because the base length is the same thing as the hypotenuse. Well, the full base right here would be the same length as that diagonal side there, because it was an equilateral triangle. So whatever this measurement is, that's actually twice the length. Okay, so I'm not going to look at it as this is half of that one. I'll actually look at it as the diagonal is going to be twice the length of the short leg that we have there. In addition to that, we're going to figure out here in a second that the longer leg is going to be A times the square root of 3. All right, now these two pieces, we should be confident that that's true, that would make sense from our equilateral triangle. All right, so let's take a look at Pythagorean Theorem, which I hope the beginning part isn't confusing, because we're going to have A, B, and C for this. Okay, but remember, A and B are the leg lengths. In our case, we've got this right here, so I'll go ahead and let that be A squared. Now, B squared, what I'm going to do is leave that as a mystery, because we get these two. Those make sense. This is the mystery one. Okay, so I'll leave that as B squared. But then C squared, I can write as 2A squared, which is important that we have the whole thing squared, because that represents the entire hypotenuse. Now, if I do square that, what I'll get is 4A squared, because you have the 2 times 2 and the A times A. Okay, over here, I still have the A squared, and that A is this A, okay? What we don't know is the B squared. So technically, the 4A squared and the A squared, those would be like terms. So what I can do is subtract that over. I can get that B squared is equal to 3A squared. When we subtract the 1 away, we get 3. And then, like the end of any Pythagorean theorem problem, what I do is square root. So B, remember that this is B, is going to be equal to the square root of 3A squared. And like the last example, because the A squared is a perfect square, that can actually be moved out front. We get B is equal to A times the square root of 3. Because the 3 was not a perfect square, it has to stay inside. And that is this. So overall, here's what we get. In a 30, 60, 90 triangle, if you have the short leg, you can double it to get the hypotenuse. You can also multiply it by the square root of 3 to get the long leg. Or you can work backwards. You could divide the hypotenuse by 2, or you could divide the long leg by the square root of 3 to get the short leg. All right, for example 2, let's go ahead and apply what we just learned here. What we have here is a 30, 60, 90. Reason that we know that is this is 90, that would be 60. So the only other angle that you could get would be 30 degrees in that spot. So you get the 30, 60, 90. The shortcuts that we have apply. And what's kind of interesting here is that you only know one side. You got the 8. That's it. And you're asked to figure out 2 more of them, which is something that you can't do with Pythagorean theorem. You just can't. But given our shortcuts, okay, this is the short leg, that the hypotenuse is actually going to be twice the length of this one, which means that y is 16. Again, you can think of these as shortcuts because they are intended to make the problems a lot faster. All right, for the x, going that direction, what we'll need to do is multiply 8 by the square root of 3, which is approximately, oh, and actually before I type that in there, the square root of 3 itself is approximately 1.73. Okay, and remember that the square root of 2 is approximately 1.41. And that is helpful information to be able to notice when it pops up in certain problems. All right, so 8 times the square root of 3 is going to give you, let's do 2 decimals. Because what I want to do with this one, which I didn't do for the last one, but what I want to do for this one is show you that this actually works for Pythagorean theorem. Okay, the hypotenuse is the 16. Let's take a look at that first. 16 squared, 256. So if I take 8 squared plus this answer here squared, which it's rounded off, okay, so be flexible with that. If we take 13.86 and we square it, we should get approximately 256, which we do. The difference is just for the fact that we did round a little bit within that spot, but otherwise it would be a perfect match. So I'm going to do one more thing here, which is called rationalizing the denominator. When we use our shortcuts, we're going to be using certain numbers like the square root of 2 and the square root of 3. Okay, and in some cases, what you need to do is divide by those numbers to get the lengths that you want. Unfortunately, in the math community, we don't like to have decimal numbers if you don't have to have them. So I don't really want to divide the 3 by the square root of 2. I wouldn't want to divide any of these because what that would require me to do is round off a number, which in example 2, you saw how that changes the overall effect of what we've got. All right, so one alternative is just to leave it like this, just to go ahead and write it as 3 over square root of 2. Okay, and 10 over square root of 2 and 5 over square root of 3. However, in the math community, we also don't like to have radicals in the denominator. We don't like it. So we have a technique which is called rationalizing the denominator that we can do, which will change these so that the radical actually ends up in the numerator. And it's a simple procedure. What you do is you take the radical that you got on the bottom and you multiply that value to the top and the bottom. Okay, so if you multiply it to the top and the bottom, you're essentially multiplying by 1 whole, because as a fraction, that would just be equal to 1 whole. That's it. Okay, so when I multiply, it does not change the value of the number because I'm multiplying by 1. However, some things change up. The square root of 2 times the square root of 2 actually just becomes 2. That's what it equals. A square root is just the number that you'd multiply by itself to get the value inside. So if I multiply these together, which is multiplying by itself, I get back 2. For the top, nothing fancy happens. You just write 3 square root 2. But in the math community, we prefer that answer over this one because it has a radical in the top and not in the bottom. All right, so then the others, they're all pretty much the same thing. Okay, whatever your radical is in the bottom, you'd multiply by that. It will become the normal form of that number. So you get a 2. The top is going to be 10 square root 2. However, sometimes when you do this, the values that you have here could actually reduce. So you can actually divide the 2 into the 10, and this can be best written as 5 square root 2. All right, for the last, we'll use square root of 3, which will give us a regular 3 on the bottom. Then for the top, you get 5 square root of 3. Does not reduce, so we leave it like that. All right, these might look a little bit worse than what we started with, except for that one. That one looks pretty good. But in the math community, we do not want to have radicals in the denominator, and this is how we can fix it. Which is important that the whole thing 2a is squared.
All right, JHS, that's a wrap on another day. If you are a bus rider, you need to make your way to the west side. Car riders to the front. Make sure your mask is pulled up.